In this video, we're going to be talking about topic 9b, Equilibria, and this is part of the Unit 2 IAS chemistry course from Edexcel. So what we should be able to do by the end of this video is you should be able to discuss reversible reactions and also being able to explain what is meant by dynamic equilibrium. We should then be able to predict and justify different effects on the position of equilibrium depending on how we change the temperature, the pressure, or the concentration. And we should also be able to look at the necessity between reaching a compromise between yield and rate of reaction when it comes to equilibrium reactions in industry. So when reactions have a small delta H or a small enthalpy value, then typically they will not go to completion. This means that at the end of the reaction or at a specific point once the reaction has been running, there is a detectable amount of reactants mixed in with the products. So we don't have a full conversion of all reactants to all products. And these are known as reversible reactions, and they're going to use this symbol here of the double-headed arrow as opposed to a total arrow. So if you have a single-headed arrow, that means that you have a complete reaction, and if it is the double-headed arrow, it means it is reversible. So an example would be the reaction between hydrogen and iodine to give you 2 moles of hydrogen iodide. The reaction between the hydrogen and the iodine is the forward reaction, so that's this one, going that way, is known as the forward reaction, and the decomposition of the hydrogen iodide, going back to the hydrogen and the iodine, that is the reverse, or sometimes the backwards reaction. So if we were to take a sample of this, we would have a mixture of our product as well as our 2 reactants. Now, when we have a reversible reaction occurring in a closed container, or sometimes use the term a sealed container, we call this dynamic equilibrium. And a dynamic equilibrium system is defined by 3 points. You have the forward and the backwards reaction happening simultaneously. So they are constantly having reactants forming products and products decomposing to reactants. At dynamic equilibrium, the rate of the forward reaction is equal to the rate of the backwards reaction. And the concentrations of the reactants and the products is constant. Now, one thing that is very important to note is the concentrations do not have to be equal. They simply have to be constant. Okay? But the rates of the forward and the reverse have to be equal. So these are the 3 points that we define a dynamic equilibrium. And this is a very common exam question, usually a 2 marker. So this graph shows our equilibrium happening. So we're looking at the rate of reaction, and we have our forward reaction will start off very quickly and the rate will begin to fall. So here we have a quick reaction and then the rate slows. And then for the backwards reaction, we have no reaction at first, of course, because we need to actually start the products, and then here the rate increases. And eventually there becomes a point where the rates are equal. And that's where the purple portion starts, so you can see right here. And this is when we get dynamic equilibrium being established. Our rates of reaction are exactly the same, and my forward reaction is happening at the same time as my backwards reaction. Now, when a reaction reaches equilibrium, the composition of the mixture is not going to change as long as the conditions stay the same. Now, this is something that we can take advantage of, and we can actually manipulate the composition of the mixture by changing the conditions. And if we change the conditions to change this composition, we call this changing the position of equilibrium. And it's either going to shift left, which means we make more reactants, or it can shift right, which means that we make more products. And we're going to look at these effects, and we're going to consider the effects of concentration, pressure, temperature, and a catalyst on equilibrium. When you are discussing an equilibrium answer, what you should be saying is what way the equilibrium is going to shift and give a short explanation of why. And we'll look at these explanations in just a minute. But again, these are very common 2, sometimes 3 markers in exams. So let's look at the effect of changing concentration. If we increase the concentration of our reactants, we're going to have more reactants available to react in the forward reaction, so the rate of the forward reaction is going to increase. So increasing the concentration will increase the rate of the forward reaction. And what that does is it's going to shift the position of equilibrium to the right to make more products. So for example, if I have A plus B giving me C plus D, if I increase my concentration of A and B, I'm going to have more particles available to collide and react, so I'm going to make more of C and D. So that's making my equilibrium shift towards the right-hand side of the products. My composition is going to change to make more of the products. As the concentration of the products increases, then we're going to have the rate of the backwards reaction increasing. Because again, if we're making more products, they are then going to decompose back into the reactants. And eventually, a new equilibrium is formed, but the equilibrium position will have moved to the right. And what that means is we're going to have a slightly higher proportion of the product compared to the initial composition of the equilibrium. So I start off with an equilibrium, let's say of I have 40% A and B and 60% C and D. Once this reaction has changed its conditions and I've changed that concentration, my reaction is going to have shifted the position of equilibrium, and so I might find that my composition of A and B has actually went down to 35%, and I have then formed 65% of my products. So my equilibrium position has shifted slightly to the right. Now, if we were to decrease the concentration of our reactant, we would then have the equilibrium doing the opposite, and we would have the equilibrium shifting to the left. Okay, so a table here is an important table in order to confirm what happens when we increase or decrease the concentration of a product or a reactant. So in order to shift the position of equilibrium to the right, I need to either increase the concentration of my product, my reactants, or decrease the concentration of my products. To shift it to the left, I need to either decrease the concentration of my reactants or increase the concentration of my products. Now, often a question will ask you to explain the change in equilibrium or the position of equilibrium, and it will link it to appearance or yield. And if you have a question like this will tend to be 3 marks. So you would have 1 mark for stating what happens to the position of equilibrium, 1 mark for the short explanation as to why, and the 3rd mark would be what effect that has either on the appearance or on the position of the yield. So if we look at the example here, my reactants are brown in colour and my products are colourless. As I increase my concentration of the OH ions, so increasing the concentration of my reactants, I'm going to shift the equilibrium to the right. So my equilibrium will shift towards my products. That will then give a higher yield of the products, and it would cause the colour to change from brown to colourless, or you may even just see it getting slightly paler. Okay, so we're increasing the concentration of our reactants, and that's going to cause a shift of equilibrium to the right, causing my colour to become less brown. If I was to increase the concentration of my iodide, then it would shift back to the left, and my reaction would appear then darker. Now let's look at the effect of changing pressure. Pressure is only going to affect gases. Similar to when we looked at kinetics back in topic 9a, and we said that pressure only affects gases in terms of the rate, it's exactly the same for equilibrium, because pressure won't affect a liquid or a solid. Their particles are already too close together. So at any specific temperature, the pressure of a mixture is going to be dependent only on the number of gas molecules there are in that specific volume. So at a specific temperature, we're going to have all the particles moving at a different energy. If I don't change that temperature, the only thing affecting the pressure is what volume they're in. So what I can do is I can increase the pressure by reducing the volume, or I can reduce the pressure by increasing the volume, depending on what I want to do. Sometimes I can look at it in terms of the number of moles, and the more moles of a gas is going to cause a higher pressure, and less moles of a gas is going to cause a lower pressure. Because of course, if you have more moles, you have more particles. Less moles, you have less particles. So when we change the pressure of a gaseous mixture, if I have the more moles of gaseous reactants in comparison to my products, when I increase the pressure, I'm going to shift to the right, because it will want to shift to the side with less gas particles. So increasing pressure shifts to the less gas moles, or gas molecules, or gas particles, however you want to phrase it. If I decrease the pressure, it is then going to do the opposite, and it is going to shift to the more gas moles. So that's the example that is in the second one in the table. If I have less gas moles of reactants in comparison to my products, my reaction is going to then shift to the left when I if I increase the pressure. So we're looking always to see what one has the most number of moles, and are we increasing or decreasing the pressure. Now, if the number of moles is exactly the same, the position of equilibrium cannot be affected by a change in pressure. Now, change in temperature is all linked to enthalpy changes. If you get a change in temperature, or if you increase your temperature, what you're going to see is you're going to have the rate of the forward reaction increasing, but you also have the rate of the backwards reaction increasing. So what happens is both of them are going to see an increase in their rate. However, you're going to see an increase more in the endothermic direction, and this is if we increase the temperature. So if we're increasing the temperature, the rate of the reaction of the endothermic is going to be much bigger than the exothermic. So that's going to cause the position of equilibrium to shift towards the endothermic reaction, because that one's going to happen more. The opposite would then be true if we were decreasing the temperature, it would be a greater increase in rate in the exothermic reaction. So we're always going to be looking at the forward reaction when it comes to whether it is exo or endothermic. What you may find is you're given something like this, so A plus B gives you C plus D, and you may be given a delta H value of, let's say, minus 50 kilojoules per mole. That minus 50 is always for the forward reaction. And if the forward reaction is exothermic, the reverse reaction is endothermic, and that is always the case. So if we have a forward reaction that is exothermic and we increase the temperature, then we're going to see a shift in the position of equilibrium to the left, because it would rather go to the endothermic reaction. If we have that same forward exothermic reaction and we decrease the temperature, it will shift to the right because the rate of reaction is going to be higher for the exothermic reaction. And then the opposite is true for the endothermic. Now, while some reactions, the low temperature is going to give us a higher yield of a product, so it's going to work in our favour in terms of the equilibrium, we need to remember that a low temperature is going to give a slow rate. So what you will probably find is that in industry, they will use what we call a compromise temperature. And that's a temperature that will give a reasonable yield, but also a reasonable rate. And in industry, companies want to make sure that not only will they be making enough of their product, but they're not going to be spending massive amounts in energy in order to actually make that product. So they have to find the balance. Now, the last effect is the effect of adding a catalyst. We know that a catalyst is there to speed up a chemical reaction, and it does this by providing the alternative pathway with the lower activation energy. In the terms of equilibrium, adding a catalyst is going to increase the rate of the forward and the backwards reaction. What is important to note here that is different from temperature, however, is that the rates are going to be increased to the same level. So whilst temperature is going to favour either the exo or the endothermic reaction, catalysts will increase both of them. Therefore, the position of equilibrium is not changed. So catalysts will not affect the position of equilibrium. What they can do, however, is they can allow a reaction to reach equilibrium faster. So if you have your reactants in a closed system and you add the catalyst at the start, you will reach equilibrium in a much quicker time than you would if you did not have the catalyst. That's where companies may use a catalyst for. It's not about shifting the yield to be more favourable. It's about, again, the energy costs and the time. Now, what we must be aware is that our predictions cannot say exactly what is going to happen when a condition is changed. So we need to understand that there is a determination of what condition is going to have the bigger effect. Now, the good thing is you are not going to be asked much about this, but you do need to be aware of our limitations. When you are making a prediction, you will only be asked about changing one factor. But in reality and industry, they have to take into account all the factors. So if we look at the example here, we've got 2 moles of nitrogen dioxide reacting to make 1 mole of dinitrogen tetroxide. And the forward reaction is going to be an exothermic. I've got 2 moles of gas on the left-hand side and 1 mole of gas on the right-hand side. So we know here that I could be changing my position of equilibrium right away, either by the pressure or by the temperature. So if we were to place this mixture into hot water, what we see is not only an increase in temperature, but we're also going to see an increase in pressure. And what we would predict here is that the position of equilibrium would shift to the left into the endothermic reaction because of the temperature, but the moles of gas and the pressure would shift it right. Now, we cannot predict which one is going to have the bigger effect at this point. Now, you will come back to equilibrium later in topic 13 and A2, but even in A2, you still don't necessarily know the effect of which one is going to be bigger. What we actually see when we do this in practice is we do see the mixture becoming darker, and what this means is that we're producing more nitrogen dioxide, so it means that our position of equilibrium has shifted to the left, telling us that the temperature has to have the bigger effect. But when we're researching the reaction, we can't possibly know that in our predictions. So what you might find a company may do is they may do this on a very small scale just to see what the predominant factor is going to be, and then they would scale it up. But there's a lot of science that goes into the fact of designing an industrial process. So when we are designing industrial processes, we have to consider the factors and the conditions that are going to allow them to convert reactants to products, but it's also taking into account the time and the energy costs. So we have to consider not only the kinetics, or the rates, but we have to consider the equilibrium and the reversibility. And typically, we are going to have this compromise to balance out the rate and to balance out the yield. So we have to have a very careful choice in our reaction conditions. So if we look at the Haber process, this is a industrial reaction that is used very, very commonly, and it is the manufacture of ammonia from hydrogen and nitrogen gas. And you can see the equation here. So the first thing that we should notice is that it is an exothermic reaction when it is a forward reaction. On the left-hand side, I have 4 moles of gas, and on the right-hand side, I have 2 moles of gas. So we can make a prediction right away about the ideal conditions, and those ideal conditions would be a low temperature and a high pressure. So our ideal conditions would be the ones that we would use to get a maximum yield. Now the problem with this is that a low temperature is going to cause the reaction to be very, very slow. And actually, we never fully reach an equilibrium because as soon as the product is formed, it is removed from the reaction vessel. In order to make equilibrium happen, you need to have this in a sealed container where we're not changing any of the conditions. As soon as we start to remove the product, what we're doing is changing the concentration. So we're not quite getting to that point of equilibrium. Now, the Haber process, scientists have determined that they use a temperature of 450 degrees Celsius and 250 atmospheres of pressure. Now, this is what we call compromise conditions. Because we've just said that we want a low temperature and a high pressure, and 450 degrees isn't actually a particularly low temperature. Now, when we have the Haber process and we have this nitrogen reacting, we know that a nitrogen triple bond is extremely strong. It has a bond enthalpy of 945 kilojoules per mole. That gives us a very, very high activation energy, meaning we will not break this bond unless we use a catalyst. Now that's fine, we know that a catalyst is going to speed up a chemical reaction, so most people's first thought would be perfect. We can still do the reaction at a low temperature, but we've got our catalyst to speed it up so we can overcome that slow rate. The problem, however, is that the catalyst does not function efficiently at low temperatures. For the Haber process, the catalyst is iron, and it needs to be at a high temperature in order for it to function at its best. The problem is, a very high temperature would be economically unfeasible. The energy costs that we require for a very high temperature are not going to be worth the money that they would make from making the ammonia. So what a company would do is they would use what's known as a compromised temperature. And that's where you have a high enough temperature for your catalyst to function efficiently, but a low enough temperature to keep your energy costs down. And the compromised temperature they decided on was 450 degrees. Again, for a compromised pressure, we said that we would want the highest possible pressure, but the problem is that it does become economically unfeasible, so we need to find the balance of having a high enough pressure to encourage the equilibrium to shift to the products, but not too high that again our energy costs are going to be too high. So the compromised pressure that was used is 250 atmospheres. The contact process is also another very important industrial process, and this is the manufacture of sulfuric acid, and this is from sulfur dioxide and oxygen gas using a vanadium oxide catalyst. And you're actually going to come back to discuss this in topic 17, which is the transition metals in your A2 year. So if we look at the information, we can see again our forward reaction is exothermic, and we have 1.5 moles of reactants and we have 1 mole of products. So due to being exothermic, we would say that we want a low temperature here, but we have the same problem as we had in the Haber process, and our catalyst doesn't function efficiently. So what we do is we have our compromised temperature, similar to the Haber process, of 450 degrees. Now, for this reaction, we don't need a particularly high pressure, because their yield of our reaction is already going to be quite high at low pressures. So we only use a pressure of 2 atmospheres. And again, that's economically feasible for us, and it's not going to be particularly high in energy costs. So let's finish off by looking at some past paper questions. What you'll tend to find is these regularly come up in both the multiple choice and the written, and it is all about identifying usually the effect on a rate or the effect on a yield or even an observation, and it's always linking it back to how is the position of equilibrium shifted. So this reaction is the equilibrium between sulfur dioxide, oxygen and sulfur trioxide, which is the contact process we were just looking at. So we want to look at what are the effects of decreasing the temperature. Now this is actually going to combine 9A and 9B. You will find that kinetics and equilibrium are typically asked in the same sorts of questions because they do have a massive overlap. So a decrease in temperature, we know from 9A, is automatically going to have a decrease in our rate of reaction. So we can get rid of A and D right away. So we know our answer must be B or C. The effect on the yield, well, we need to look at the fact of is it exo or endothermic, and we've got a negative enthalpy, so our forward reaction is exothermic. So if we decrease the temperature, what we find is that rate of reaction is going to decrease, but we have it a little bit less for the exothermic, so that is going to be our favoured reaction, shifting the equilibrium to the right, giving you a higher yield. So your answer here is B. The effects of increasing the pressure. Well, increasing the pressure, we know from 9A is going to increase the rate. So this time it's either going to be A or D. And increasing the pressure, well, we have 1.5 moles on the left-hand side and 1 mole on the right-hand side. So increasing the pressure is going to cause the equilibrium to shift to the lower amount of moles, which means it's going to increase the yield. So our answer is D. And there you go, B and D. We'll also look at the June 2018 paper. This is an example of a written question on chemical equilibrium. So the gases nitrogen dioxide, or NO2, and dinitrogen tetroxide, N2O4, form an equilibrium at room temperature. So we have 2 moles of reactants and 1 mole of products, and our forward reaction is exothermic. So for 3 marks, we're saying that a gas syringe containing the equilibrium mixture is compressed by pushing in the plunger and then allowed to stand with the plunger in the new position. Predict how the appearance of equilibrium would change during this procedure. Okay, so what we need to think about is what's happening, how is my equilibrium shifting, and what will I see? So when I first pushed in the plunger, what I'm doing is I'm reducing the pressure and I'm actually increasing the concentration at that first point. So what we first see is we see the mixture getting darker. So it initially goes dark because I'm increasing the concentration. So I'm increasing the concentration of my reactants here. Now that it's left to stand, what you will see is the mixture will then become paler, or you can even say it will become colourless. And the reason for that is the equilibrium is going to be shifting to the right. And why is it going to be shifting to the right? Well, because we have less moles on the right-hand side. So the right has less gas moles. So you can see that we are discussing what we see, what way the equilibrium has shifted, and why. Those are the 3 key points that you have to be hitting for an equilibrium question. For part 2, this is just a simple state and explain the effect of the increase in temperature on the equilibrium. Well, we know the forward reaction is going to be an exothermic, so if I increase the temperature, I'm going to see my endothermic reaction being favoured. So my equilibrium shifts this time to the left, and it shifts in the endothermic direction. And because it is for 1 mark, we don't need to go into any more detail than that. We simply say that the equilibrium is shifting because it would prefer to be in the endothermic reaction. You could even say because it goes away from the exothermic or because the forward reaction is exothermic. Either one would be accepted. And for part B, where we've got the potassium chromate 6 is dissolved in water and equilibrium is set up. And the position of equilibrium is well to the left, so our solution appears as an orange colour. We're adding the aqueous alkali and we see the solution turning yellow, and we want to explain this observation. So if we think back to our 3 points, we said we should be explaining what we see, what way the equilibrium shifts, and why. Now, they've already given us the first one, which is why this is only a 2-mark question. So they've removed the observation mark because they tell you the observation. So why does it shift? Why does it turn to a yellow colour? Well, that's because the equilibrium shifts to the right. And we can see that in our question. It's telling us that we have a yellow colour, but we need to explain why that happens. So when we add in an aqueous alkali, what we're actually adding are OH minus ions. So what we're doing here is we must be getting some sort of reaction with the OH minus. And when you look at the equation, you should automatically be drawn, I hope, to this term, your hydrogen ions. When hydrogen ions come into contact with hydroxide ions, they are going to react and they are going to form water. And that is exactly why our equilibrium is shifting, because as the hydroxide react with the alkali, they are decreasing in concentration. So we can say the alkali, or the OH ions, react with the hydrogen ions, and that decreases, or decreasing, their concentration. And that reaction would be written out like this. Now, if you were to explain this in terms of the water, because yes, we are going to make more water, therefore my concentration of water is going to increase, that would not get you the mark. The reason why is you're not explaining where that extra water comes from. You have to say that the alkali reacts with the acid and then it forms the water. So they will not give you a mark for just saying the concentration of water increases. So we're removing the hydrogen ions because they're reacting with the OH, so our equilibrium is going to shift to the right. And there's your mark scheme for those final answers. That's everything for topic 9b, Equilibria. Hopefully everything has made sense. I would strongly suggest that you practice these questions using past papers or the textbook and go over the 2 and 3 markers and just get the technique into your head. If there's anything you're not sure about, please feel free to leave a comment below, and we hope to see you back soon.